In this video, we'll be talking about the ways in which you can interweave transactions in a way that doesn't have the same sorts of conflicts that we talked about in the previous video. The ordering of the parts of transactions, the interweaving of them together, is called a schedule. So in practice, transactions often run concurrently, meaning they're running at the same time with other transactions. So the correctness principle that we talked about before about it should appear as though there's one transaction that goes from beginning to end and then there's another transaction that goes from beginning to end doesn't apply directly. But by just allowing multiple transactions to occur at the same time, just like letting them do whatever they want, it's likely to lead to an inconsistent state. It's likely if you have a rule that says, no account should go into negative amounts of money, but you allow for multiple transactions to occur without checks, it's very likely that somebody could double spend. Somebody could have $100 in their account and they give 60 to person A and they give 60 to person B. And if those transactions are running at the same time, it could be that after those transactions are done, he actually has a negative amount of money when in reality, one of those transactions should have failed. So we use the notion of schedules to basically say which transactions can occur at the same time, which ones are allowed without leading to an inconsistent state. For instance, transactions which don't touch the same parts of the database are very likely to not actually lead to problems. Like if I need to add a new teacher to the employees data table, and I need to add a new student to a particular class, unless there's some relationship between the employees and the students, both of those transactions could occur simultaneously without any problems. And so a schedule is the sequence of actions taken by one or more transactions, which seems a pretty appropriate name. So for a good part of the rest of this class, I'm going to be using a much more simplified notation instead of writing like, here is a SQL query that inserts into this table, and here is a SQL query that gets out these rows, and here is a SQL query that modifies these rows. Instead, I'll be doing a much more abstract version of this thing reads from a part of the database. So when I say read parentheses A comma T, it's basically saying it's reading the element A from the database and storing it in the variable T. Now, what is an element? An element is really a part of the database. It can be a table, it can be a row, it can be a particular field within a row. It doesn't really matter for these purposes. It's just a part of the database. So when I say read parentheses A comma T, it's basically saying I'm reading, let's just imagine row A and storing it in the T variable. And I can also consequently write to the database, doing an update or an insert. I'm doing some sort of change to element A. So I can say write element A T saying set the A value to the value of variable B. So it's just a way to easily write I'm reading from A and then I'm writing to A. And so we have two transactions here that I have written. One is called plus 100, one is called times 2. And so the way that these transactions work is they're modifying two elements in the database. So the first transaction reads from A, makes the number that it got 100 bigger than it used to be, and then writes that new value to A. So now A is 100 larger than it was, and it does that same thing for B. And the other transaction looks almost identical, except what it does is it reads from A, doubles that value, and then writes back to A, and then reads from B, doubles that value, and then writes to B. And so our consistency constraint is the promise that the element A should always be equal to element B. Okay, and now we can check if our transactions maintain that consistency. So if our database is in a state where A and B are the same, do either of these transactions break that consistency? No, because the first transaction adds 100 to both of them, and if you add 100 to both of them, are they still equal to each other? Sure are. The other transactions doubles both of them. If you double two numbers, are they still equal to each other? Sure are. So if transaction on the left occurs first, and then transaction right occurs next, after those two transactions, A will still be equal to B. If you reorder them, A will still be equal to B. And I can show that to you. I mean, it's not too hard to understand, but I want you to be really clear with the notation that I have here because it's going to get a bit more complicated after this. So what I have here is on the left side, the left transaction, and when those actions take place, this is time read from the top downwards. And then I also have when transaction 2 happens. And then I have, the state of the parts of the database A and B. So let's assume A and B both start off at 25. The database is in a consistent state because they're equal to each other. And why is them being equal to each other the consistency constraint? I just made that up. I just said that is the rule for my database. And because these transactions don't violate it, I have a promise that it should be the case at the end. So they start off both at 25. I read from A, which is 25. I add 100 to that. And then I write to A. So now, after this write state, after the write state right here, A is 125. And now I read from B, add 100 to that, write to B. And now B is 125. Now I could have just repeated 25, 25, 125 all the way down. But you can just assume if I don't say what the state is, it means it's unchanged from a previous state. Okay, so after the first transaction's done, the state of A and B is both 125. And now I start working through this transaction, the doubling transaction. I read 125, double it, write 250. I read 125, double it, write 250. And so then at the end of our two transactions, I have the database in a consistent state. I have it, both the database elements at 250. Okay, so that's if the left transaction occurred first. But of course, transactions that are occurring at the same time, it could have been just by chance that the right transaction got in, 10 milliseconds faster, and it is going first. And so if transaction 2 goes first, you guys can follow it quite easily. I'm sure I don't have to walk you through it, but A gets read, A gets doubled, B gets read, B gets doubled. Now they're both 50. A gets read plus 100, now it's 150. B gets read plus 100, now it's 150. And now both A and B are 150. And now, is the database consistent? Yes, both A and B are the same. Now, once again, like before, the order that transactions occur does matter. The ending database is different whether transaction left or transaction right happened first. That's not under dispute, but the thing is that the database is still consistent. The rule that I said need to be followed, that A is equal to B, it still holds. Once again, if you care that the left transaction should come before the right transaction, then what you should actually be doing is one long transaction, because the rule is within a transaction, you always have to do each action from beginning to end. So once again, if order matters, make it all in one transaction. If order doesn't matter, you can have separate transactions. Okay. So the fancy name for what those previous two schedules were, they're called serial schedules. A schedule is serial if its actions consist of all of the actions of one transaction and then all of the actions of another transaction. No mixing of actions allowed. We did all of transaction A and then we did all of transaction B, or the reverse. The really nice thing about serial schedules is they're guaranteed to preserve consistency because each transaction occurs in complete isolation. There's no way for transactions to interact with each other if one goes from beginning to end without any other actions taking place. This is the stupidly simple version of making sure that you have isolation between your transactions. A schedule is called serializable if there exists a serial schedule which would achieve the same final database state. What were the final database states? And in the previous example, we can go back, the final database state of 250 and 250, or the final database state of 150 and 150. So if other schedules, and there are other non-serial schedules, which we'll talk about in a little bit, other schedules are called serializable if, when all is said and done, the database is in one of those two states, one of those states that could have been created by just a normal one after the other serial schedule. And another way of saying this is a serializable schedule, and putting the database in a state just like if one transaction occurred in isolation and then another transaction occurred in isolation. If a schedule is serializable, it means that it by definition passes the acid test. All right, so let's look at some non-serial but serializable schedules. It's really important to understand the distinction. A serial schedule actually says all of transaction A, then all of transaction B. A serializable schedule just says after all is said and done, after all, whatever the schedule actually is, it looks as though that is what happened, that the final database state is if it had been just A and B, or just B then A. So here is a serializable schedule, but it's not a serial schedule. So these are the same transactions from before. And what if I did part of transaction doubling? So I take A and double it. So 25 gets doubled to 50. And then I read A and add 100 to it. Now A is 150. And then I read B and double it. I get 50 here. And then I read B and add 100 to it. I get 150. And now my final database state is 150 and 150. Is that the same as one of the possible serial schedules? Sure. I mean, like I just showed you the previous example where they could get to both be 150. So is this schedule serializable? Yeah, because it achieves the same result in the end. Now, is this a serial schedule? No, because we have this weird mixing of actions. It's not that one transaction occurred from beginning to end and then another transaction occurred from beginning to end, but the end result was the same. So the nice thing about serializable schedules is that they preserve consistency because it looks as though each transaction occurs one after the other. But even if you don't want to be the very simple serial A and then B, you can make serializable schedules that have the same external effects. So let's go to our first multiple choice question here. With 3 transactions, so in the previous examples there are only 2 transactions. With 3 transactions, how many possible serial schedules are there? So with 3 transactions, how many options do you have for your first transaction? Well, it can either be A, B, or C. And then how many options do you have for your second transaction? Well, it has to be one of those other 2. And how many options do you have for your last one? Well, there's only 1 left, so it has to be that one. So that's 3 times 2 times 1, that's 6. It's how many permutations are there of the 3 serial schedules. So the correct answer here is 6, the second answer here. Okay, slightly different question. With 3 transactions, how many possible serializable schedules are there? And the correct answer here is there's no way to know because each transaction can have a bunch of smaller steps within it. You can't know if there will be each transaction is only taking one action within itself, so it's just 6. But it could be millions if each transaction has 100 steps in them, and you can interweave all of those steps separately. Okay, so we talked about serial schedules. We talked about serializable schedules, which could be mixed up, but as long as their end result's the same. There are also non-serializable schedules. So these are schedules that can produce states or effects on the database that would not have occurred if these transactions weren't interweaved, weren't mixed up with each other. Non-serializable schedules violate isolation, the isolation principle in ACID. And I'm going to be showing you a schedule that's non-serializable. And schedules like it, non-serializable schedules, are the thing we're trying to avoid. Non-serializable schedules means transactions aren't really transactions. Transactions have to be scared that other transactions are going to mess with their data as they're working with it. So let's look, and here is the same 2 transactions as before, but I've interweaved them slightly differently. So I start with the doubling transaction. I read A, double it to 50. Okay, that's fine. And now I'm doing the plus 100. I read from A, which is now 50, add 100, I get 150. Great. I read from B, which is 25, I add 100 to it, I get 125. And now I finish the doubling transaction. I read from B, which is 125, I double it, I get 250. And then, so what is our final result of our database? Our final result of our database is 150 and 250. Now note, this violates consistency. It violates our consistency constraint that A should be equal to B. There's no way for one transaction to violate our consistency constraint. However, mixing them up in this non-serializable way, it comes up with an outcome that we could never have gotten by a serial schedule. This is a non-serializable schedule. This is bad. This is what we're trying to avoid. Okay, so you might go, well, how do you tell if a schedule is non-serializable or not? Or even the more complicated question, how do you make serializable schedules that achieve the performance that you want? And that's what we're going to be working on in this class. Okay, so I just have to warn you that sometimes the exact steps that are taking place within a transaction determines whether a schedule is serializable or not. Now, what do I mean by that? Let's imagine that I had two transactions that look almost identical, except one transaction adds 100, another transaction adds 200. And I have the exact same starting here, messing with A, messing with A, messing with B, messing with B. And now, when I interweave these two transactions, I read from A, add 200, read from A, add 100, read from B, add 100, read from B, add 200. The outcome from this schedule is a serial schedule's output. Like if I did A first and then B first, I would have got this result. If I did B first and then A first, actually in this example, I would have also got this same result. And so the fact that instead of not doubling here, that I'm just adding 200 here, means that for this particular set of transactions, this interweaving was actually completely fine. This is a serial schedule. This kind of happenstance, this like, oh, the fact that it really doesn't matter if you add 100 to a number and then 200 or add 200 to 100, is something called an arithmetic coincidence. All right, so in this case, one transaction was adding 100 to A and B, another transaction was adding 200 to A and B. Because of the commutability process of addition, the order and interweaving of these transactions doesn't matter. It doesn't violate serializability. And so once again, this is called an arithmetic coincidence. And so it would be really great if SQL could look at your two transactions and actually figure out, oh, this transaction is trying to add 1 to this number, and this transaction is trying to add 1 to this number. It doesn't matter which one adds 1 to the number first, so I'll just let both of them proceed. The problem is this is very difficult for a scheduler. The scheduler is the part of the program that's being handed these transactions. It's very hard for the scheduler to be able to identify, oh, these transactions both are reading and writing to the same parts of the database, but they're okay. So, unfortunately, SQL is a very complicated language, as I'm sure you guys are all experiencing in the homework, and these transactions can often involve other programming languages and other sorts of interactions. And knowing what effects they would have on the database, knowing how these effects would interact, knowing what are allowed and what not, is incredibly difficult. In fact, it is as difficult as every other incredibly hard problem in computer science, like the halting problem. So really, the things that the scheduler is using to make its decisions is it can see the parts of the database you're trying to read from, it can see the parts of the database you're trying to write to, and thus it has some idea of the sorts of things a transaction might do. And so what it does is it makes an assumption. It says basically anytime you write to the database, it's going to assume that the value depends on the database state in such a way that no arithmetic coincidences occur. It can't use the fact that 100 plus 200 is the same as 200 plus 100 to kind of help itself. So even though when writing these schedules by hand, you might be smarter than the scheduler because you can see, oh, this order doesn't matter. In general, we don't actually care exactly what's being written to. We just assume that the thing's being written to is unique, is some way not connected to these sorts of chance encounters.